So hopefully everyone can hear me okay. So yeah, good morning everyone. Apologies for the change apologies for the change in plans. As I said, I'm replacing Ian this morning, and I've kind of merged what would have been my talk after his talk, which was going to focus just on energy storage applications, and I've kind of merged it with some work that I do on polymer nanocomposites, as well as hopefully giving a bit of a general introduction to 2D materials, to nanomaterials, to graphene, a bit of history, and a bit of commercial perspective as well, because the vast majority of the research that I do and the work that I do is industrially sponsored or working directly with companies. So as James said, my name's Mark. I'm a reader in nanomaterials in the Department of Materials, and I'm based here in the National Graphene Institute. I also have some labs over in the Henry Royce Institute, just out the window there. So as James mentioned before, we're all here because this paper was first published back in 2004, 20 years ago this year, that was discovering the amazing properties of graphene. So graphene as a material had been theorized that it would be thermodynamically impossible. You can't isolate a single atomic layer of this material. What Andrei Kostya and colleagues did was actually mechanically exfoliate these flakes, build some devices, and find out it had these amazing electrical properties. So it was really the discovering of these electrical properties that kind of started this explosion of interest in nanomaterials and 2D materials. And then there was almost endless superlatives that kind of kept on coming on about it being it was the thinnest imaginable material because it was only a single atom thick. It had the highest specific surface area because it was so thin as well. It was optically transparent to light, so it could be used in transparent displays. It had the highest mechanical properties ever tested of a material, very high modulus, very high strength, yet it was still mechanically flexible. It had record high electrical and thermal conductivity. It was an impermeable barrier, and it could be easily functionalized. So as a single material, it seemed to open up this plethora of different application areas. Based on any one of these would be amazing. But I think really what makes graphene or even related nanomaterials like it quite interesting is multifunctionality. It's that in terms of applications, we can combine multiple benefits, not just one, and that's really what makes it competitive or what makes it advantageous over other materials which might have only one of these advantageous properties. Of course, this led to, in 2010, the Nobel Prize in Physics for Andrei and Kostya, and people started imagining things like having an elephant balanced on a pencil could be supported by a single monolayer of graphene. Of course, things like that are nice to theorize or hypothetically imagine. What people very quickly found is that scaling up from a few microns of this material to a square meter of it that was defect-free, perfect, and easily transferred, and etc., was much more difficult. So that sort of the journey of scaling up these materials has been quite challenging. But as James said, it's really a large family of materials. And there are lots of applications, even for, say, the lower quality materials that are cheaper and more readily produced. So in terms of production methods, I'm sure many of you are aware, and we have some of the companies here today that do this. There are lots of different ways to make graphene, and they range in sort of different amounts of quality or also price in terms of mass production. So in the top right-hand corner, you've got the highest quality. That's the mechanically exfoliated, the work that's done in the clean rooms downstairs here, where you have a very clean environment. You normally take some adhesive tape and you're basically peeling off your layer of your crystal one layer at a time. That's great. You can get very beautiful crystals from this. You can do some amazing research, but you're never going to commercialize that. You're never going to scale that up. You're never really going to make devices out of it like that. The opposite end of the spectrum, you've got things like liquid phase exfoliation. This can be done through processes like high shear, through ultrasonication, or even electrochemical exfoliation, where you're taking your material, your bulk material, your graphite, in the case of graphene, you're dispersing it in a solvent or an electrolyte, and you're applying some kind of energy. That energy is then exfoliating the layers off, and that's great for applications like coatings, composites, inks, energy storage, transparent conductive layers, even biological applications. So that's why a lot of the commercialization we've seen is using liquid phase exfoliation to produce the material because it's much cheaper. And even though the quality, might be much less than, say, mechanically exfoliated, it's certainly sufficient for the applications that we're interested in. In between that, you've got things like chemical vapor deposition, CVD, which is where you're growing your graphene or your other 2D material from the bottom up. So you're taking usually a gaseous precursor, you're taking a metal catalyst, high temperature, and you're actually growing a thin film of this. That works really well. It has been scaled up a lot. You can even get roll-to-roll growth of this. The challenge there is getting it off of the catalyst. Once you're growing this material on your metal catalyst, you really want it on something else. You want it on glass, you want it on a polymer, something like that. So quality is very high, but it's still quite expensive for what you want to do. Then you've got more niche applications like molecular assembly, where you're basically doing organic chemistry to stitch these molecules together, or you've got from silicon carbide as well, which is also very good for electronics, but can be quite expensive. So in terms of the journey over the last 20 years where it's gone, if you look back at 2004, as I said, what people could do was exfoliate maybe a few square microns of this material, and that was great if you could stick it under a microscope or an AFM or a micromanipulator, but you couldn't really do much but make a prototype device. You fast forward only 6 or 7 years, Samsung started doing CVD over very, very large areas up to A4 or even A3. So in only a few years, you've really gone from not visible to the naked eye to large sheets of it. And then in 2020, Axtron had this roll-to-roll CVD graphene system where you can now continuously grow graphene on a very continuous way and then transfer it onto other things as well. So in only sort of 10, 15 years, you can really see you've gone from microns of a material to meters of it and almost endless of it depending on your system. So it really has come a long way, and as James said, in terms of some of the liquid phase things, to produce powders or to produce inks or dispersions of this has gone from sort of the gram scale to the multi-ton scale over the last 20 years as well. There's still a lot of academic interest in graphene. As James said, today is really about the academic research and the fundamental work we're doing on it. If you look at the number of papers from Web of Science that use the word graphene, in 2004, there was, well, maybe one or two. And then over the last 20 years, you can see this has basically skyrocketed. So now, I think COVID kind of flatlined it a bit, but hopefully that will start to come up, or it might be that it's kind of peaked at about 40,000 publications per year. But that's well over 100 papers a day coming out on graphene. So it's an incredibly studied material. I think every university, every lab, every country around the world is working on this material. And so it's quite nice that, that Manchester is the home of this material and that we're still kind of leading the academic research of it. As I said, in terms of the applications of graphene, it's got all of these amazing properties in terms of electrical, mechanical, thermal, etc. So it really has almost endless application areas as well. You've got things like optoelectronics, using it as a photodetectors or in photovoltaics and solar cells. You've got transistors and photodetectors, particularly high frequency ones. You've got sensors, you've got multifunctional sensors that might be chemical sensors, that might be light sensors, that might be electrical sensors. You've got biological applications such as drug delivery, biosensors, artificial skin, medical implants, things like this. Flexible electronics has been a big thing recently, where you've got touch screens, touch panels, bendable phones, bendable laptops, things like this. And in particular, you've got things like energy storage, so batteries and supercapacitors, which is obviously one of the things I'm going to talk about today, and also composites and membranes, where you've got lightweight, strong composites, and multifunctional composites. So it's really these two areas which I'm going to cover because that's kind of what my research embodies. Other speakers later today will kind of cover some of these other areas as well. Because of that multifunctionality, I think when you look at applications of a material like graphene, you can take two systems like automotive and aerospace, and you can really look at, even in a single car, where is it that graphene can find an application? And it's really almost everywhere. You've got things like being added to the elastomers in the car tires to improve tear strength and improve performance. You've got them being added to the body itself to improve mechanical strength, to reduce the weight, to increase fuel efficiency. You can have it in the glass as a demisting because it can be electrically conductive and transparent. You might have it in the LEDs, you might have it in sensors, you might have it in electric vehicles in terms of batteries or supercapacitors. Really everywhere within automotive, you can find applications for this material because of all of those different properties it has. And same for aerospace, things like lightning strike protection or structural health monitoring, lightweighting. 50% of, say, the A350 is carbon fiber composites. That carbon fiber can be improved by adding graphene to it. So as planes are moving towards more composite structures, graphene is going to find more and more of an application in improving the mechanical strength, reducing the weight, increasing the fuel efficiency, and helping that energy transition and decarbonization as well. So a lot of the work that I do is really, as I said, is aimed at covering those two application areas. I think it's important that we discuss what we mean when we say graphene as well, because technically there are some standards that were produced that say that when we say graphene, we really mean monolayer of carbon, we mean defect-free oxygen, 0% oxygen. But in reality, when you commercially buy graphene, or even in academia, when you publish papers on graphene, it can actually be a large family of different materials that kind of colloquially get referred to as graphene, even though technically that was incorrect. Because of course you have monolayer, you can stack this together and have bilayer and have trilayer, so these are commonly referred to as few layer graphenes. And then of course you can stack these together, and then you've got graphite, which is of course the base material. But then you've got like a subset of materials like these graphene nanoplatelets, which might be sort of tens of nanometers thick. So that's clearly much more than 10 layers. So it's essentially graphite, but it's very large lateral size. So it might be on the order of 20 odd microns, but only a few nanometers thick. So its very high aspect ratio is really what makes it behave differently than, say, bulk graphite. Even though technically it's not graphene because it's many layers thick, its behavior is very different. So that's kind of why it's a subsection of these materials. And then you have ones like graphene oxide, where you have a lot of oxygen functionalities on the surface, which is normally chemically introduced, and then you can even remove these and have reduced graphene oxide. But this has very different properties. So graphene, as I said, has very high electrical conductivity, very high thermal conductivity, good mechanical properties. Graphene oxide is an electrical insulator because each of these chemical functionalities acts as a defect site, scatters the transport of electrons and phonons, so its electrical and thermal conductivity is much lower. Its mechanical properties are much lower because of these acting as defect sites on it as well. So the benefit of it is that it's water soluble. So graphene is very hydrophobic, doesn't like water. Graphene oxide, very hydrophilic, likes being in water. So it's water processable, so there's kind of the trade-off in properties with it. So what that means is we really have this kind of very large parameter space where we can look at the properties of the material that we're using for a given application. You've got the lateral size of it, you've got the carbon to oxygen ratio, you've got the thickness, the number of layers, and that kind of gives us this sort of wide variety of materials, which again, colloquially or even commercially, these might all be referred to as graphene, but the wrong material is going to give you the wrong results. So if you're adding graphene oxide to try and get electrical properties, it's not going to work. You're adding an insulator. The same as if you want good mechanical properties and you're adding very, very small flakes, that's not going to give you very good reinforcement. So one of the sort of take-home messages is you need to use the right material for the application that you're using. And knowing what the right material is isn't always straightforward. And so sometimes there is a certain degree of having to do some research, do some studies to understand, is the material I'm using going to give me the benefit that I'm actually trying to get in that application. So as James said as well, graphene was just the first of the 2D materials that was kind of explored. That was quickly followed by a variety of others. The first one being hexagonal boron nitride, HBN, which is structurally very similar to graphene, but has very different properties in that it's a wide bandgap semiconductor, so it's completely insulating. It's white as well, so sometimes it was referred to as white graphene. Its mechanical properties and thermal properties and things like this are close to graphene, but not quite there. But that does find a lot of applications in thermal management, which I'll talk about later on as well. And then there's functionalized graphenes as well, like graphane, where it's hydrogenated or fluorinated. Then there was a lot of other ones. There was the transition metal dichalcogenides, like molybdenum disulfide, niobium diselenide. You've got superconductors, semiconductors, and then also the family of MXenes or titanium carbides, or other ones like this as well. So there's really been, we've gone from having a single pencil in our pencil case to having all of these different materials, having all of these different properties, which we can then either combine. So there's, as they said, the physicists like to actually physically stack these together, make a new material, take a conductor and an insulator and a semiconductor and make a device out of those. But even material scientists like myself who do things a bit more crudely can combine multiple materials to get some synergy out of that. So it's not just purely the one material. We can get some sort of added benefits by having a combination of these multiple materials. Often people ask me, well, you've spent all this time on one material, you've found a bunch of others. How many 2D materials are there? There was a study a few years ago now on theoretically just basically finding out how many 2D materials exist structurally, looking at the crystal structure, and they found that there's actually well over 1,000 2D materials that exist or can exist. And so far, scientists, we've spent over 20 years basically understanding the properties and applications of one of these materials. And so basically, we're all going to be here for much longer working on this because there's still a lot more to uncover, a lot more to understand, and a lot more applications that can be unlocked by these 2D materials. So yeah, it really is still a very rich research area. And even though it's kind of transitioning from academic research into commercial production and applications, there really is still a lot of fundamental questions that we don't know about even graphene that we're still uncovering. So it's still quite an exciting area to be doing research on. So that's kind of the background or the introduction I wanted to give. Now, I thought I'd talk a bit more specifically about my research and the work that I do. As I said, these materials have so many different application areas, and as a material scientist, I can't decide what I want to work on, so every day I like to work on something different. And that graphene kind of provides a perfect platform for this to work on a sort of a very wide variety of application areas. So my research group does everything from carbon fiber graphene composites. We look at coating individual carbon fibers or glass fibers or aramid fibers and looking at that interface, looking at 3D printing of graphene and other nanocomposites, making the filaments as well as the properties of the actual printed structures, flexible coatings, looking at the interaction between, as I said, carbon and glass fiber on different length scales, energy storage, things like electrochemical supercapacitors, producing graphene by electrochemical exfoliation, which is quite a nice technique to do it. Membranes, or looking at the filtration or ionic rejection we can get by stacking these 2D materials, making battery anodes out of these, or even 3D printing aerogels, which can be used for catalysis or other applications as well. So even within one research group, you can have a very broad and very multidisciplinary application areas for this one material, which is really what makes it so interesting, for me at least. So the first of these I want to talk in a bit more detail. I'll give some specific examples, is polymer nanocomposites. So as I said, multifunctionality is really the name of the game with this. When you look at polymer nanocomposites, really you want a combination of different benefits. You want it to be lightweight, you want it to be strong, you want it to be stiff, you want it to be electrically conductive, you want it to have a good interface, you want it to be thermally conductive, you want it to have all of these benefits at once. And really what we've found is that to achieve these multifunctional benefits, it's about that synergy. It's about the combining multiple nanomaterials together and not just any one. So when we look at, say, older nanomaterials, we've got like 1D materials like carbon nanotubes, or 0D materials like carbon black. These are sort of traditional conductive additives that might be used. So when we're looking at, say, electrical conductivity, we thought, okay, let's look at the combination of graphene nanotubes and carbon black. Let's see how they interact with each other. Let's see if we can get any synergy from them. So there's a lot of demand for conductive polymers. There's a lot of application areas, everything ranging from anti-static coatings through to EMI shielding, this Internet of Things, that if every device in our house is on Wi-Fi, or if our cars are all talking to each other, we really need to make sure there's not getting interference between these devices. We need to make sure they're well shielded. There's not getting any problems with that amount of EM radiation that's going around. But we still want to make them out of plastic. So that means we need to have conductive plastics. So being able to tune the conductivity of our polymers is very important. So for those familiar with this, you will have seen these electrical percolation curves. This is when you plot the conductivity of a material versus the loading of whatever additive it is that you're adding. You kind of have a very abrupt step change where you have an insulating material where your filler, your graphene, your nanotubes, your carbon black, whatever it may be, are dispersed in your matrix. They're not in contact with each other, so there's no conductive pathway, so it's still completely insulating. As you keep adding more and more filler, you reach this certain critical threshold, this percolation region, where all of a sudden you have a continuous pathway through your composite, and now you have electrical and thermal conductivity through it so the conductivity shoots up and then it more or less flatlines. So understanding the shape of this curve depends on the dispersion of your filler, how well these mix, how well they disperse. It depends on the aspect ratio. Are they very long and thin? Are they more likely to make contact with each other? It also depends on how you make it. Is it hot pressed? Is it injection molded? Is it spray coated? Whatever it may be. So there's a lot of different properties that we can play around with to change the shape of these curves to make it interesting to industry. Because what industry don't want is when they buy a master batch and they're making these, they don't want to add slightly not enough polymer or slightly not enough filler and it's not conductive, or maybe it's too conductive. They really want to have it a bit kind of idiot-proof that if they give a customer the recipe and say, this loading, this filler, this mixing method will give you the properties you want. So they don't want it to be too sensitive. So we thought, let's have a look at how we can change the shape of this curve, but then also how do carbon blacks and nanotubes compare to graphene, for example, and is there any synergy between them? So the way we did this work is we took 3 model materials. We took a carbon black, Ketchum black, used to be made by Axo, now made by Neurion. We took a graphene nanoplatelet from XG Sciences called C750. We took some carbon nanotubes from NanoSil. And we said, okay, let's make individual composites out of these in polycarbonate, twin screw extrude them, hot press them, and then do a bunch of characterization to understand the conductivity of them. So we started off by making individual fillers. So we make these percolation curves for just the nanotubes, just the carbon black, or just the graphene. And as you can see, the nanotubes and the carbon black percolate at a very low filler loading, less than about 1%. They become conductive very quickly. In this particular graphene doesn't become conductive until 8% or so, or even more. And to understand why, you do an extra analysis of the morphology. If you look at the TEM images here, you can see this carbon black is reasonably well dispersed. You've got particles that are everywhere. You can obviously see that as you increase the loading, you're going to get some kind of continuous pathway. The graphene, in this case, the GMPs, are very agglomerated together. They're not very well dispersed. They're sticking to themselves more than they are. And so that agglomeration is basically why you need to add a lot of material before it becomes conductive. Whereas the nanotubes, these ones in particular, disperse very, very nicely, have very high aspect ratio, and that's why they form a conductive pathway very, very easily. So understanding how your filler disperses, understanding how well it disperses, what interaction it has with the polymer matrix, and also inherently the properties of its aspect ratio are crucial in understanding its actual electrical conductivity. We also did some theory, some modeling of these based on what the predicted aspect ratio should be on the percolation threshold. And you find that for the GMPs, theory predicts that it should be around sort of the aspect ratio to be 14 to 30. And that's roughly what we're finding. The model predicts that there's going to be a lot of agglomeration, and that's exactly what we see. These conductive AFM images show you've got these essentially isolated conductive islands that are not in contact with each other because there's no connected pathway. And so that's why you need, again, a much higher loading. For the nanotubes, have a very, very high aspect ratio, over 150. So these actually much better to disperse, again, much better connected. The carbon black behaved a bit differently than we expected. There's obviously some clustering, but we actually, because of the way it clusters or the way it interacts with itself, its individual particle aspect ratio isn't what's important, it's the cluster aspect ratio. So that one, we have to kind of adjust our model to take that into account. That's kind of a bit beyond what I want to talk about today. So as I said, we then looked at, okay, let's look at the synergy between these. So we went away, poor PhD student made about 100 different master batches of these materials in different ratios. So we looked at combining carbon black and nanotubes in all these different ratios, carbon black and graphene in all these different ratios, nanotubes and graphene in all these different ratios. And that basically allows us to build up this whole parameter space of, okay, is there any unexpected benefit? Is it purely just a sum of the parts where, okay, if this one gives us this conductivity, this one gives us this, we meet halfway in the middle? Or is there an unexpected benefit by having the two of them interact with each other? And so that basically allows us to make a curve that looks like this, where you've got out here, you've got 100% GMPs, down here you've got 100% nanotubes, and up here you've got 100% carbon black. And then the data points in between are the different ratios. So this one's carbon black and GMP, and these ones are carbon black and nanotube, and these ones are nanotube and GMP. So you can see basically, depending on each of those 3 fillers, you can modify the amount that you have in it to change where your percolation threshold is, but also this critical exponent T, it changes basically the shape of this curve. So not only can you shift where percolation occurs, you can kind of flatten it out a bit or change the dimensionality of that network, and that will change the sort of the conductivity, if you will, or change how sensitive it is to variations in the processing technique and things like this. So that's a good example of how we can use graphene and other nanomaterials together to modify electrical properties. If we move on to, say, thermal properties, thermal management is in particular very important for electrical applications, where you have basically you have a heat sink, either in, say, an electric vehicle or a CPU in a computer or anything like this. Basically you want to get heat out of it, you need to have some kind of thermal interface material in between these. One of the possible candidates for this that's very attractive, as I said, is boron nitride. Boron nitride is electrically insulating, so you don't need to worry about it short-circuiting it, but it has still a very high electrical conductivity. And you can also get boron nitride nanotubes the same way that you can get carbon nanotubes. And so again, looking at this synergy, instead of having just boron nitride nanosheets, we can have boron nitride nanosheets and nanotubes, so a 2D and a 1D material interacting together, and that gives us this synergistic interaction where we get better thermal conductivity. So this work was looking at them in epoxies as a thermal interface material, and we can see this is the thermal conductivity of the neat epoxy, and as we add more nanosheets, or when we have a composite of nanosheets and nanotubes together, we see a difference of the in-plane and through-plane thermal conductivity as well, whether we're going this direction or that direction. That's because these are hot-pressed, so you do get some alignment of all of your fillers. They're essentially horizontally aligned, so in-plane you normally have a much higher thermal conductivity. But you can see by adding these fillers, you can get approximately 1,000% increase in the thermal conductivity from your bare epoxy. So it really is quite a nice application of these 2D materials where you still maintain that electrical resistivity, but you're getting that thermal conductivity out of it. You can also do this with graphene. This has been done by companies like Huawei had a phone that was doing this, making these basically graphene heat spreaders. So traditional mobile phones and laptops use graphite as a heat spreader. And often people say, well, what's the difference between if I have graphite or I take graphene and restack it? Why would that behave any differently? And it really all comes down to the stacking interaction. In graphite, each of your carbon layers are very strongly interacting. They have this AB stacking, this Bernal stacking. If you take graphene, you disperse it and then restack it, you basically get a random orientation between it. And that random stacking basically gives you a very weak interaction, a layer-to-layer interaction. And what that does is actually give you better thermal conductivity. So graphite, you get thermal scattering, or the layers are kind of connected to each other. If the layers are independent of each other, the thermal conductivity is higher. And that's why these materials are of benefit. So this work we were doing, we were taking some electrochemically exfoliated graphene oxide, and we were actually getting rid of those oxygen molecules. And so you've got essentially a reasonably defective graphene layer. You stack them together, it looks something like this. These are the individual flakes. These are stacked as a thin film or as a coating. And this is the sort of laminar structure of these layers. And then we pyrolyze it at about 2,000 degrees, and that restores these defects. That completely gets rid of these carbon vacancies or any other remaining oxygen groups on there, etc. And you get back to a very nice, pristine carbon structure. You can see this Moira pattern that you get between the layers interacting with each other, showing that it's very defect-free. There's no atoms missing or dangling bonds or anything like that. So even though it's defect-free, we still have that absence of that stacking order that you would get in graphite, sorry. So we've still got the layers are kind of independent of each other. And so that means that obviously we can get very high electrical conductivity of these foils. So the electrochemically exfoliated graphene oxide starts off with the conductivity about 10 to the 4. As we heat it up to 2,000 degrees and we repair all these defects, we can get conductivity of over 170,000, which is quite nice. In terms of thermal conductivity, we can see we get this over 200 watts per meters Kelvin, which is very, very high, much higher than we would get for, say, even for graphite. So it makes it quite attractive for use in heat spreaders. But because we've got this electrical conductivity, it's also very good for EMI shielding, because these layers can reflect or dissipate electromagnetic waves. And so this is an example of the EMI shielding efficiency versus frequency for graphene oxide or reduced graphene oxide. This is the commercial requirement, around 30, and this is what our material gets, about 36 decibels. So this is also thickness dependent, and so we can make these much thinner. So this is 8.5 microns thick, which is very thin. Is actually quite close to being competitive with, say, metallized films as well. So again, this single material is excellent thermal conductor, electrical conductor, and that gives us these multifunctional properties or benefits like EMI shielding, which can be quite nice. Moving on to, say, structural components or structural applications. As I said, you've got areas like lightweighting or structural, where traditionally these composites are made with glass fiber and carbon fiber. So a lot of this work, what industry wants to do is understand, okay, how do we, if we add graphene into these systems, into glass fiber or carbon fiber, can we get any added benefit from it? And again, it can be sometimes an unexpected benefit. So this was some work that we were actually doing with Petronas, which is a Malaysian energy company. We were coating carbon fiber with graphene nanoplatelets from a spray coating process, making composites out of this, and then looking at the barrier properties. So for things like pipelines or for gas storage vessels, for hydrogen storage, for example, you obviously want your composite cylinders to be able to block that gas. And we find that by having very, very small loadings of GMPs, this is 0.05 volume percent, we can actually get a significant reduction in the CO2 permeability through it. And that's because you kind of got this added tortuosity that the gas molecules can't pass straight through it. They take much longer because they run into these flakes that are impermeable. So by adding only a very small amount of material, you can sometimes get these barrier properties that you might not have expected, which is quite nice for a lot of different applications. You can also look at, say, the mechanical applications of this. This was looking at glass fiber, again, coating these. One of the challenges that came up initially is for a lot of glass fiber or even carbon fiber is done through a process called resin infusion, where you might basically add your graphene into your resin and try and infuse it like this. The problem with that is that you actually filter it out. The fibers themselves block all of the graphene, so you don't get a really nice dispersion of your filler. And so in glass fiber, you can see that visually because you get your black on one side of it and a very poor dispersion. So again, that's why we were using this spray coating method where we're not relying on it, this filtering effect being a problem. And again, when we're looking at the mechanical properties of these composites, we find that very low loadings give us the most benefit. So we see improvements in the modulus and also the strength at low loadings between about 0.2, 0.3%. And again, if you add too much material, as you can see visually from the SEM here, what you're doing is you're introducing additional defects. You're basically introducing another interface that's going to fail when you're applying mechanical strength to it, mechanical load to it. So you want a little bit of material to give you benefits, but not too much that it starts to become detrimental. And that's generally what you'll find when you talk to companies or any of this material that's being commercialized. It's that understanding just the right amount to give you the properties that you want. This can also be scaled into different kinds of, it's not always just flat coupons. This is some work we're doing here on braided carbon fiber, which is used, say, for pipelines or for making gas cylinders, or it can also be used for like wind turbine blades or things like this. So we have these robotic winders, which we can coat these carbon fibers in graphene. And again, we see, say, in terms of compressive strength, the control, the modulus, the strength of it basically goes up quite significantly by having graphene integrated into it. So we're getting this synergistic improvement that at a very low loading of graphene, less than 1% usually, we can get this big improvement in mechanical properties over just carbon fiber or just glass fiber, which is quite impressive. The other area that we see a lot of benefits or a lot of improvements is in dynamic measurements. So there's thousands and thousands of papers out there on mechanical properties of graphene composites. Typically, they're only looking at static measurements, where they do a single stress strain curve, but they're not looking at, say, creep, where you have a continuous load over a prolonged period of time, or fatigue, where you have a cyclic load being applied again and again and again. So again, this was work that we were doing that was sponsored by Petronas. We were looking at, this is glass fiber composites with functionalized graphene. So again, this is looking at how, as we functionalize the material, can we improve the performance or the interaction with the matrix. So this was amine functionalized graphene, and it's in an epoxy, so you get sort of a chemical interaction between those materials. Spray coated on like we have in our other cases, and again, so you can control the dispersion. And what we find is, this is the sort of the static measurements, what you'd expect to see that as you increase the content up to, say, 1%, you get a more or less linear increase in the tensile strength and the modulus up to a certain level, and then it flattens out. These are at different temperatures. This is at room temperature and then at higher temperatures. And of course, as the higher temperatures get closer to the glass transition temperature of your matrix, in this case an epoxy, it can soften and then actually reduces its mechanical properties. So what we actually found was that graphene was more beneficial at those higher temperatures instead of just at room temperature. That the slope of this line basically is steeper at higher temperatures. So we would see more benefit when your matrix was starting to soften. This was very evident when we look at creep measurements. So this is creep at different temperatures and at different loadings. So the control here at very high loadings, we took 175 megapascals. It's failing after about 2 minutes. Adding just 0.25% of our material doubles that to almost 4 minutes. Going to 0.5%, now it lasts about 9 minutes. Adding 1%, now it lasts 264 minutes. So it's the same glass fiber composite. All you're adding is a very, very small amount of this material at the same load, and you're actually getting a massive improvement in its service life. So of course, at more realistic operating loads, these ones here are going tens of thousands of minutes, basically longer than we were allowed to use the machine for, whereas these ones here are failing 29 minutes, and this one here, 4,700 minutes. So that creep, where you've got a continuous load is really, even if the benefit in a static measurement might only be modest, in terms of these continuous load applications, which, that's what's important for industry. If your composite is under load, say it's in an airplane wing, you want it to last the whole flight, not just takeoff. And so understanding those properties at those longer lifetimes is very important. And it's the same for cyclic load. If we look at fatigue, where you're constantly loading and unloading a material, particularly also at higher temperatures, the control one here, we can see this is a SN curve. This is basically the stress before failure versus the number of cycles for failure. And so you get a curve like this. The red one shows it with 0.05% of that graphene oxide, functionalized graphene oxide at 90 degrees. And some of these are lasting millions of cycles before they're failing. And so because this is a logarithmic axis, that's actually a significant improvement in the fatigue behavior of these composites. So it's not just the modulus goes up or the strength goes up in a single measurement. These actually, in real world conditions, give us much better benefits than we may be expecting. So hopefully, I've still got a bit of time. So in terms of, that's what I wanted to talk about in terms of polymer nanocomposites, in terms of multifunctionality. Moving on to the other half, which is electrochemical energy storage. One of the biggest challenges for energy storage is, graphene seems like an ideal material. It's got high surface area, it's highly electrically conductive. Why is it not everywhere? And one of the problems is, particularly for top-down production methods, if we take graphite, we exfoliate it, we produce a nice dispersion or a powder or whatever form it may be. We've got this really, really nice high surface area material. And now I want to integrate that into my battery coating line or my supercapacitor, which means I make an electrode out of it and it restacks. So I lose all of that really nice high surface area that I wanted. So I'm lucky if I get maybe a few hundred square meters per gram, which is nowhere near the 2,500 square meters per gram I was promised. So there's really a big problem here. It's not graphene's fault. It's the way that we're trying to use graphene and integrate it into our application without modifying the way we actually do that. So what we need to do is prevent that restacking, either frustrate it somehow. People have done things like crumpling these graphene sheets up into like a bowl, like a sheet of paper, or having other materials in there as well. So maybe if going back to what we've learned about synergy, by having multiple materials in there together, we can prevent that restacking occurring. I also said in terms of the way we produce this, our group does a lot of work on electrochemical exfoliation. It's a very popular way to do it. It works essentially like a lithium-ion battery does, where you take graphite, which is used as an anode in batteries, you apply a potential in an electrolyte, and you basically get these ions that force their way in between the layers. That expands the interlayer spacing. If you keep on applying potential, you keep on forcing more and more ions in there, or larger ions in there, you basically push these layers completely apart. So what you can get is a structure like this. So this is a graphite foil. It's partially exfoliated, and then we stop the experiment. And you can see that each of the layers is being slowly pushed apart. And obviously, if you keep on going, you can completely exfoliate this, or you can tune the amount of exfoliation or that interlayer spacing, depending on which ions you intercalate into it. So one of the ways we can set about preventing this restacking is actually taking that material, exfoliating, and leaving it on a foil. So essentially like device like this, where you've got a graphite foil, you're exfoliating the surface of it to get this really, really nice high surface area. You then backfill that with your electrolyte. In this case, it's a polymer electrolyte. So now you've actually got a nice solid state flexible device, which you could, say, integrate into biosensors, into clothing. You could have it on fabrics, whatever it may be. And you can actually get these sort of flexible and wearable solid state devices. So that's an example of how, by modifying the way we think about, say, a supercapacitor or we think about an electrochemical device, we can actually develop newer technologies that take advantage of what graphene inherently is already giving us. We get added benefits that, in terms of preventing that restacking, if we can functionalize the surface with other molecules, we can improve their performance as well. So when we do this electrochemical exfoliation in ammonium persulfate, which has this structure, we introduce some nitrogen. Actually, we nitrogen functionalize or nitrogen dope the graphene at about 1%, just pretty mild amount of doping. But what we find is that gives us the pseudo-capacitance. So normally capacitors, this would kind of be a very nice square curve, which tells us the amount of energy we're getting out of it. These added peaks here are because we're introducing this nitrogen into the structure, and that gives us a higher capacitance. So we can get around 250 millifarads per square centimeter, which is pretty good. Normally, commercially, anything over about 100 or so is kind of where you're interested in these devices. So as well as tuning the surface area, tuning the performance of it, by having this surface functionality or by functionalizing it, by the way we produce it, we can get added benefits in the actual performance. We can take that a step further and actually deliberately do additional functionalization with other molecules during the exfoliation. So we do the standard electrochemical exfoliation where we have our graphite in solution. We normally have an electrolyte which has, say, a sulfate ion in there. But we can also have some these aryl diazoniums. Aryl diazoniums are a molecule that very rapidly and very quickly react with sp2 carbon, like graphite, graphene nanotubes, things like this. And that allows us to have these aryl groups on the surface, which again are going to prevent that restacking, but also introduce other functionalities. So we can have a nitro or a bromo group to get that added pseudo-capacitance. And so if we make a device out of this exfoliated functionalized material, for graphene, its capacitance is very, very low. It's down here at about 3 or 4, basically not very good. If we functionalize these, we see this massive improvement, particularly at low scan rates. But what we do see is that it drops very quickly, at least in the case of the bromo case. In the nitro, it's better. And that's really the trade-off between pseudocapacitance, that yes, the energy you're getting out is much higher, but it's a slower process. So as soon as you increase the current density, which is the same as increasing the cycling rate, the rate of charging or discharging, the performance can drop quite quickly. So these are good for low power applications where you need high energy. And so one of the ways we can visualize this functionalization, as well as seeing the electrochemical performance, we get different colloidal stability. So I said at the start, graphene is hydrophobic. It doesn't like being in water. It collapses out. If we exfoliate it in the presence of this diazonium, we can functionalize it and actually make it nicely water stable. Well, this is in water and isopropyl alcohol. So after 7 days, it's very nicely stable. It's not sedimented out. And that makes it more processable. We can use it as inks. We can use it in printing. We can use it in coating, things like this. And for the zeta potential as well, we see graphene is basically close to 0, but these ones have a much more negative zeta potential, which makes them much more stable in solution. I won't go into this. This is just using Raman spectroscopy to look at the effect of doping, or to kind of, again, verify the introduction of these functional groups on the surface. We see that the peaks of graphene are shifted, both by a combination of mechanical strain, because you've got this functional group on there, but also doping, where it's either electron withdrawing or electron donating from the surface. So that gives us this spread where we can basically, using Raman, determine how functionalized our material is, combine that with how stable it is in solution, and then what kind of electrochemical performance we expect to see from it. Okay, so that's one way we can prevent restacking is functional molecules. As I said, the other way to do it is synergy between, say, multiple materials. So if we combine, say, graphene or MOS2 by themselves, their performance is not very good. If we mix the two of them together, we immediately get this synergistic improvement. So that was work that we did, this is quite a long time ago now, almost 10 years ago. We've expanded that to looking again at, now if we functionalize the graphene or if we functionalize the MOS2, can we get even further benefits? So here we were taking MOS2, we were chemically exfoliating it by intercalating lithium. We were taking electrochemically exfoliated graphene, mixing them together to get this composite structure where you've got stacked graphene and MOS2. And so you can see actually from TE how these stack together. So you tend to get very large graphene sheets with smaller MOS2 sheets basically decorated all over the surface. And so that gives you a very nice high surface area where the MOS2, which is a semiconductor, has good capacity but not very conductive. You've got this nice electrically conductive backbone in the form of the graphene. So that's why you get this synergistic benefit that the graphene and the MOS2 prevents the restacking, but you've got a highly conductive backbone. And when you can look at these, again, the capacitance of the composite structures where you're combining them is much, much higher than if you have just the pure MOS2 or even just pure graphene. And so that really shows the synergistic interaction between them is very beneficial for energy storage applications, and you can tune it and you can understand how that works better for whatever commercial application you need it for. Also with cycle life, that the graphene by itself, after cycling, the structure remains basically the same. These functionalized materials, you can see, have a much higher available surface area. You're basically preventing this restacking of these layers collapsing in on each other. Higher available surface area gives you much better performance. So this is just quickly to say, hey, you can also do this where you're electrochemically exfoliating your MOS2 as well as your graphene. So you've got your MOS2 exfoliated and your graphene exfoliated. And in the same way, now you can, again, you've just got more parameters, more variables here to form these kind of layered stacked structures where you've got alternating MOS2 and graphene that can be functionalized. And again, the performance of these is usually much better than the single or individual material. You can get quite large flakes here. So this is the MOS2, where it'd be very thin, only a few nanometers. On the graphene here is a bit thicker, this flake, but much larger lateral size, as you can see. And so that's how you can get this interaction between the different layers. Finally, last couple of ones I want to talk about is MaxeNes. So we said at the start, MaxeNes are kind of the new flavor of 2D materials that have been around for a few years now. They are a bit like graphene in that they're a very good electrical conductor. They're normally metallic conductors. They're 3 layers thick, normally in the case of here. You normally have titanium and some carbon atoms as well. They're much more solution processable. They can be handled in water. So in this work, we were taking these MaxeNes, exfoliating them, and actually 3D printing them into these kind of structures, and then freeze drying them to remove the solvent, and getting a very, very high surface area aerogel structure, which is really good for, again, for supercapacitors, for energy storage applications, where you can see here that the capacitance, we're getting a very ideal sort of structure, so there's no pseudocapacitance, it's very stable, and the capacitance is much higher than, say, pure graphene material, but if you start looking at composites of these, you can get added benefits as well. So 3D printing is one of the ways to rethink about, we said that the problem with energy storage is when you make a coating of these, you restack them, that ruins their properties. 3D printing and aerogels is a way to prevent that restacking actually through the way that we actually make the composite structure. Finally, in terms of batteries, graphene is already used a lot as a conductive additive in lithium-ion batteries. This can also be combined with silicon. Silicon is very interesting for batteries because it has such a high capacity. The problem with silicon is that obviously it's not very electrically conductive, and it also has a massive volume expansion. It can be over several thousand%. So by actually interleaving graphene with silicon particles, the graphene can absorb that expansion without failing, without breaking, but provide that electrically conductive backbone. So by making these structures where you've got these composites of graphene and silicon or silicon dioxide together, you can get these performance which is much higher, the capacity is much better than just a single material, and the stability, it lasts much longer and is more stable than silicon would be by itself, or with carbon black, which is a traditional additive. So again, that's looking at how graphene as an additive can really improve the performance of some of these materials. And it's not usually used by itself. Commercially, lithium-ion batteries use nanotubes already, but it's carbon black and nanotubes. And now companies are looking at carbon black and nanotubes and graphene, that tertiary mixture, because of the different benefits you get from each of those components. So with that, hopefully that was not too fast. Hopefully I've summarized here that graphene and also the other related 2D materials have a lot of amazing abilities. but it's really the combination of them that really makes them stand out. So it's not when you add just one material, it's when you add multiple materials together, that synergy. But it's also, you need very little of these materials. That, you know, a lot of the applications, the optimal loading that you need is less than 1%. So yes, even if graphene is expensive, you only need a very small amount of it to get pretty significant benefits out of that, which is why we're seeing it commercialized so much, which is why tomorrow you'll hear lots of companies that already have a lot of products out there that are using it. With that, I'd like to thank all of my group members. I'd like to thank Ian as well for getting sick and allowing me to give this talk. Thank you to all of the companies that I work with, all the different funders, both the government research agencies, but industry as well, and all of the PhD students and postdocs in my group that did this work. And thank you very much for your attention, and I'll happily answer any questions.
Thanks, Mark. Thanks for stepping in as well. Appreciate it.
That's all right.
I guess really as part of this 2 days, we're going to talk a lot about sustainability and net zero.
Yeah.
Could you say a few words about end of life and life cycle analysis for composites and energy?
Yeah, I mean that's something that isn't very well understood and is something that we're actively studying at the moment. So, you know, carbon fiber composites are difficult to recycle as they are already because, you know, you either need to basically burn off the matrix or chemically get rid of the matrix, and then the fibers themselves are damaged and they usually end up getting chopped up, and then it's chopped fiber, which is a lower application for the next time it's used. What people even understand even less is if I take a graphene or a nanotube composite, how can I recycle it? Can I chop it up? If it's a thermoplastic, can I melt it down? So we have several projects on that right now, understanding if we take these nanocomposites and we put them through traditional mechanical recycling, what happens to the dispersion? Does the presence of that nanofiller actually compensate for any degradation to the polymer matrix? So if the molecular weight of the polymer is reducing with each cycle, does the presence of the graphene in there actually counteract that? So it means the polymer can be recycled for more cycles without needing to add additional virgin material to compensate for that. And so far, all of the evidence seems to suggest exactly that the nanofillers in there, they get dispersed better each time it cycles. Each time it gets chopped up and made into a new component, its performance is getting better because you're dispersing it, and it's getting better. So far, it seems to be very highly recyclable, which is nice to know.
Again, if anyone from industry's got interest in life cycle assessment, there are some interesting programs and schemes. I talked to one of the team. John?
Thanks, Mark, for the good overview of all the applications. Just as a general view, someone who's been around kind of development of graphene 2D materials for some time now, what's your general view on the rate of acceleration and adoption of nanomaterials in a variety of applications?
Yeah, I mean, I think now, even in the last few years, we're seeing a lot more applications that are using graphene or using other nanomaterials. I've always said that the real sort of killer applications are when they don't do a lot of publicity around it, when they don't, you know, it's a competitive advantage for them to have graphene in their product. They don't need to go around saying, oh, this uses graphene, because their product is just better than their competitors. They don't need to explain how or why. And that's really what we're seeing now, that there's a lot less press releases or a lot less hype around it, and just we're seeing better products lasting longer, and it's getting more of those applications. We're also seeing a consolidation of suppliers that before, you know, I think with things we're seeing there was kind of an explosion of them. Now we're seeing them more consolidate and be more focused in different areas. Even the ones that are out there though still produce very different morphology materials. So you do need, you know, a variety of suppliers using a variety of exfoliation methods, because of the different applications or the different requirements that they need for that material. So, yeah.
Thank you so much for
That's right.
the presentation. I have a question about the thermal conductivity. You showed
Yeah.
thermal conductivity increase in flame.
Yeah.
That there's a dramatic increase.
Yeah.
Think about the true thickness.
Yeah.
It's very challenging.
It is, yes.
Everybody mentioned, in the literature also, we see lots of in-plane conductivity.
Yeah.
But they do not describe the differences here.
Yeah, in our case, the real difference for that anisotropy is because these are hot pressed. So because they're hot pressed, we're forcing alignment horizontally, which is why we see much better thermal conductivity in one plane. The idea was that if the boron nitride nanosheets, which are flat and two-dimensional, more or less align that way, can the nanotubes kind of form interconnects between those vertically and allow that kind of three-dimensional structure? We see some degree of that, but it's still very difficult to control the morphology within a matrix like that. So I think there's still a lot more work to be done, either to maybe covalently attach, say, nanotubes and graphene perpendicular to each other, or boron nitride, so that you can get that added through-plane thermal conductivity as well as the in-plane, which kind of happens naturally. So yeah, I think there's a lot more work done to kind of improve control the alignment to give you the thermal conductivity in the direction that you want it.
Thank you very much.
Right.
My name is Klaus Radberger, company Lu from Germany. When we look at technologies like battery technology, photovoltaic technology, we see that China is a very, very strong player and even ahead of the rest of the world in that instance. How about the graphene technology and also commercialization? How do you see the European status in that? Are we at the same level as the Chinese and Asian players?
Yeah.
Are we behind them? I know that in battery technology, a lot of graphene nanoplatelets is thousands of tons even is produced in China. I don't see any European player producing thousands of tons. So how do you judge that?
Yeah, I mean, and definitely in terms of batteries, a few years ago in particular, China was just, the volume of electric vehicles that were being made there was far in advance of anything that Europe or North America was doing. And so that meant that there was a lot of investment around conductive additives like graphene into the. In terms of now, I think that maybe, particularly post-COVID, that seems to have, that the rest of the world has caught up to a certain degree, that we're seeing North America, Europe, places like this, even South America, doing a lot more domestic production. We're seeing a lot more, scaling up of graphene, particularly places like Canada, places like Southeast Asia outside of China as well, that the graphene production has really scaled up. And everyone wants to have a domestic supply of batteries as well because of, security reasons and geopolitical reasons. So I think that, yes, China definitely in terms of batteries had a massive head start, but now I'm seeing that I think that's kind of leveling out to a certain degree, or that Europe and North America are really caught up in terms of the volume and scale that they're producing. I mean, China still does a lot in terms of volume and is still doing quite well. But in terms of the technology that goes into it, a lot of it is still being developed in North America and Europe. And so, China has the advantage in terms of scale, but maybe less in terms of the actual new technology being developed. It's just that the challenge is making sure that it gets exploited in North America and Europe instead of China.
I think hopefully over the next 2 days you'll see more about the local supply chain and how you can also take graphene from waste, so you're not necessarily dependent on some other materials.
Yeah.
Any other questions before we break? Kamsa?
Hi, Mark. Thank you very much for the insightful presentation. Myself, Dr. Kamsa from the Graphene Manchester. So you showed agglomeration with increasing loading.
Yeah. Yeah.
You also observe agglomeration in carbon black plus GMPs, or I guess CNT plus GMPs.
Yep.
And what do you think? What could be the features or aspect of GMPs that is actually governing the agglomeration? Is it just a dispersion, or is it a flex size, or anything?
Yeah, it's kind of a combination of things. The main things is the morphology of the flakes. So if you have very thin flakes, they're basically more easy to crumple, they're more easy to wrap around themselves, and the actual effective aspect ratio you get in a composite is less than when you look at the flakes as a powder by themselves, because they're basically too flexible, they roll up on themselves, and they end up having a lower aspect ratio. So you want your flakes to be slightly thicker so that they're rigid, that they hold their shape. It also depends on the chemical functionality. You want them to basically to have a strong interaction with the matrix, so that they don't want to stick to themselves, to avoid that agglomeration, so they can disperse nicely and basically get the matrix completely coating them to basically get that mechanical properties. For electrical, that's bad because you actually want a certain degree of agglomeration. So it's kind of tricky to balance, how do I get enough agglomeration that I form a percolating network, but also do I get it dispersed enough that it's, I'm using as minimal amount of material. But yeah, it's the morphology, the loading, and the surface functionality. So it's quite complicated.
Observe any carbon black plus?
Yeah, definitely. There's synergy between them. That it comes down to the rheology as well. That when you have these very high surface area materials, the polymer itself can start to become very viscous, very difficult to process. And then it comes down to the engineering side of tuning your process conditions to make sure that you can actually process that very viscous material without damaging it, without destroying the flakes or destroying the nanotubes or whatever they are in there as well. So there's a lot of balancing you have to do between getting the right amount of dispersion and getting it to the properties that you want out of it. That's right.
Okay, any final question? One final question?
I was just thinking in terms of the circular economy, if we can make most of the components in a car, for instance, how do we consider like the circular economy? I was thinking maybe in terms of graphene, for instance, or other methods that they can use to make it quicker recycle.
Yeah, absolutely. I mean, as James kind of mentioned, that traditionally, okay, we think of graphene being produced from graphite as a precursor material, but you can use almost any hydrocarbon as a precursor. You can use waste material, you can use waste plastics, you can use biomass, you can use petrochemical byproducts, things like this. And so you could actually have, there are a lot of, there's a cost and scales of economics in there as well. But you can produce graphene quite cost effectively and quite high quality in areas where you don't have access to that graphite as a precursor. So in terms of automotive, yeah, you could have it that all of the components in that could be produced domestically, so you're not having to import large amounts of graphite or graphene for batteries or for composites in the actual car itself. You could actually be using waste plastics from older cars as a precursor to make the nanomaterials for the new generation of cars.